welcome again. We're going to do some more podcasts of the Flinn Scientific reaction prediction process today, or this session. I'm going to pretty much finish up AA to the end is what I'm going to attempt to do here. Hopefully time will permit in that regard. So let's go ahead and begin. I have to find the right slide, so I'm going to take a second here because it's not obvious. OHH, we got to keep going back here till I find AA. Be patient here. X, Y, Z, AA. There we go. This should be AA coming up here. Yep. All right. Excess chlorine gas. So chlorine, of course, is Cl2. Is passed over hot iron filings. So that would be iron. So here we have a classic example. We have two elements that are going to have to do redox. So the iron, the chlorine, is going to become chloride. All right, this is going to go to chloride. I'm not going to put on the product side just yet. And the iron, that's going down in charge, and then the iron is going to have to go up. And of course, you should know that the charges of the iron likes to go up to either a +2 or +3 charge. Commonly, it's +3, so it's going to make FeCl3. To balance that, you'll need to put a 2 here, 3 here, and a 2 here. What type of reaction is occurring? You could probably call this a synthesis reaction, but you could also call it a redox reaction because it is definitely both a redox and an oxidation reduction reaction, and a synthesis reaction. Letter BB, magnesium metal, is added to nitrogen gas. This is a similar kind of a deal. Of course, the magnesium, you've got two elements. This is just like that last one. He's going to go to a +2 charge, and he's going to go to a -3 charge, so you get Mg3N2. I remember a couple of years ago on the AP exam that they gave this. I've seen this reaction before. So you need a 3 here, and that's it. What's the oxidation of the magnesium before and after the reaction? Mg is 0 before, and Mg is +2 after. So that's not too bad. You need to know that, really. One thing that's kind of interesting about these problems is they're kind of giving you some hints in the question, is the final solution acidic, basic, or neutral? For example, in CC here, it's probably not neutral. So, all right, so lithium hydride. Now, this is a little trickier one because you have a hydride. Now, hydride's a weird thing. Hydride is H-1. So this is with solid, so it would be LiH. And it reacts with just simply water. Now, when you take hydrides and you put them in water, hydrogen, the reason you haven't seen hydride very often is because it's just quite an unstable compound, or species, I should say, or ion. And so this is going to make the lithium, the hydrogen is going in the hydride is going to go to H2, and that leaves, if you think of the water technically as HOH, that leaves you with the Li and the OH minus. And of course, by doing this, you are, by definition, making the hydroxide, which makes this a base. And by the way, oxidation reduction, the hydride is going from -1 to 0, H2, with a 0 charge, and it's going from -1 also up to +1, which is the H in the OH, because you have to have something go up and down. Pardon me, this lithium should be a positive charge. I just realized I made a mistake. All right. And then the DD, benzene. Now, benzene is treated with bromine in the presence of a catalyst. I don't think they're going to give us an OChem question. Now, if you remember benzene is C6H6. It's this cyclic ring. I think it's totally acceptable to draw it like this, all right? And it reacts with bromine. That's Br2. And so I think it's not a bad idea. What's happening is that if you draw C6H6, it looks like this, right? Draw it here for you, and you've got an alternating double bond, and off of each of these comes a hydrogen, right? Well, the carbons are quite strongly held. It's sp2, by the way, hybridization, and when you react this with the bromine is going to react and do kind of replacement with one of the hydrogens. And so you're going to get, what's going to form. I can only think of this structurally. It's hard to do it, otherwise. This is going to make a Br. The little circle means it's that ring. And then you've got all the H's off, and then that kicks out HBr. So one Br kind of takes place. It's kind of like a single place. Classify the type of organic reaction. Again, I'm not sure you're going to see a lot of these organic reactions, but we call this a substitution reaction. All right? The next one, double E. solid lithium oxide, so it's solid, so it's Li2O. Remember, lithium has a positive 1 charge, and O minus 2, so that's why it's Li2O, is added to excess water. These ones, I think, very, very likely going to appear on the test. This is a metal oxide. Metal oxides plus bases, plus water, make bases. And so it's going to make the, what's the base with lithium? It'd make lithium hydroxide. Now, I can't write it like that because, of course, lithium has a positive charge, and because lithium, all lithium salts are soluble, and so this is the reaction. Now, this is not balanced. If you think of this as HOH here, I think I'll do it that way. It'll make it easier to balance. I've got one OH, and I've got this H, and so I'm going to need a 2 here and a 2 here. Is that right? Yeah. And of course, it makes a base. If you make hydroxide, it by definition is basic. All right. All right. F here. Solid potassium chlorate. So that's KClO3. Potassium has a positive 1 charge, and chlorate has a minus 1 charge, is heated in the presence of manganese dioxide. If they heat it, this is actually just a catalyst, MnO2. This is a classic reaction. I think we've seen this. How many moles? Okay, what's going to happen is that when you heat up something that contains oxygen, it actually is going to make potassium chloride, the salt and oxygen. Chlorates, when heated, do this. I'm not sure this is a tough one. And to balance it, you're going to need to put a 2 here, 2 here, and a 3 here. How many moles of reaction products can produce from 1 mole of potassium chlorate? A little tricky. If you've got 1 mole of this, how many mole of products? Okay, then you would multiply 1 mole of KClO3. All right, let me do this again. 1 mole of KClO3 over 1. And then you would say 5 moles of product versus 2 moles of reactant. So it's 5 over 2, or 2.5. And I could live with a question like that. All right, dilute hydrochloric acid. So we dissociate it because hydrochloric acid is a strong acid. Is added to a solution of potassium sulfite. Sulfite is SO3 2 minus. Don't confuse that with sulfate, which is SO4 2 minus. SO4 2 minus. Here, it's like a double replacement reaction. The potassium and the chloride are spectators. They're going to fall out, and H and SO3 are going to get together. This is not a strong acid. H2SO4 is a strong acid, but H2SO3, this is sulfurous acid, is a weak acid. The spectator ions, I've just crossed them out. Of course, the potassium and chloride is the answer to this one right here. All right, we're on HH. A solution of sulfuric acid. Now, sulfuric acid is kind of a weird deal here. How do you deal with sulfuric acid? You could either write it as H positive plus SO4 2 minus, but because actually the HSO4 minus ion is weak, but the first ionization is strong, you could also write it as H positive plus HSO4 minus. It's kind of it sort of depends on the question. But let's say, is added to barium, a solution of barium hydroxide, strong base, so Ba2 positive plus OH minus, probably 2 OH minus, until the same number of moles of each compound has been added. So let's actually put the 2 here, because that's going to make a difference. So we've got the 2 H's, and actually, I think I'm going to do it with the bottom one, plus Ba2 positive plus 2 OH minus. So we've got the same number of moles of each compound. The 2 hydroxides will neutralize both hydrogens. So you're going to make 2 waters plus, and they're going to make the precipitate barium sulfate. Is the cyanide solution basic, acidic, or neutral? You made water and barium sulfate. And since you've done it in what we'd say stoichiometric ratios, or sort of the equivalence point, then it says explain too, it's going to be neutral. I thought most of them were going to be. This is neutral because you have neutralized all of the acid. II here, okay? II. All right, a mixture of solid calcium oxide, CaO, positive 2, right? Ca has a positive 2 charge, and O is minus 2. And solid tetraphosphorus, that'd be P4, decoxide, O10, is heated. All right, now we have a metal oxide and we have a non-metal oxide. All right, when you make a metal oxide, a non-metal oxide, it's going to make a salt that contains oxygen. Now, you got calcium, you got calcium, you got oxygen, you got phosphorus. Or maybe I should say Ca and then P and O. So you got Ca and P and O. Now, this is going to become a polyion, so there's two polyions that can become PO4 3- phosphate or PO3 3-. Which one will it be? It's going to be the one that keeps the same oxidation number as the phosphorus that we have here. This does not change charge or oxidation number, so we got to figure out what the charge is here. So you've got 4x minus 20, O is a charge of minus 2, equals 0, so x is 5. So which of these two has an oxidation number of 5? I believe it's the phosphate. We'll just try. You'd have to do both if you don't get it wrong, but it'd be x minus 8 equals negative 3 for the phosphate, and that is the positive 5. So it's going to be calcium phosphate. Calcium phosphate, kind of a weird deal, Ca3PO4 2, of course, because calcium with its 2 charge and phosphate with its minus 3 charge. Now we've got to figure out how to balance this. This is going to be a little bit tricky, but you're probably going to have to double this. That's going to give me 6 of those, and that gives me my 4. Yep, that's it right there. Okay, is this product soluble in water? So the question is this a soluble compound? Well, what about phosphates? What do you know about phosphates? Phosphates are generally insoluble, so this is insoluble. You would make a precipitate in this particular reaction. That's a little... All right, the JJ question. Sulfur dioxide gas, SO2, if you want to put a little G here, is passed over solid calcium oxide. Guess what? This is just like that last one. We have a non-metal oxide in the sulfur dioxide and a metal oxide in the calcium oxide, so we're going to make a compound that has Ca, S, and O in it. Now, SO, there are 2 varieties of polyions with sulfur and oxide, so it's SO4 2- or SO3 2-. When you have a simple one like this, you've got O2 and O, like, like P4 weird, you can just kind of add them together. It's just CaSO3. Name the product. That, of course, is calcium sulfite. You don't have to put the 2. You don't have to put the Roman numeral 2. You would be wrong to do that because, of course, calcium always has a positive 2 charge. All right, 2 more, looks like. KK, solid zinc sulfide, so that's ZNS. That's an insoluble compound, by the way, okay, is heated in excess oxygen. Okay, now you've got oxygen here with no charge, so he's going to have to acquire a charge. In fact, look at the question. What change in oxidation state does the sulfur undergo in this reaction? So they've just given you a hint. The sulfur is going to change its oxidation number. Well, and so will the oxygen. Or the O is at 0 and the S is at minus 2. So they're going to both have to change their charge. So when you put S and O, the O can go to minus 2, right? And the sulfur can go to lots of things, actually. But it's going to make the gas sulfur dioxide gas. And that's going to lead with you the zinc. It's not going to make zinc metal. Why you can't make zinc metal? Because then you've already, one thing's gone up and one thing's gone down. So it's going to leave zinc oxide. Now, I believe to balance this is a little trickier than it looks like. I think you need to put a 2 here, a 2 here, a 2 here, and a 3 there. And the sulfur went from minus 2 up to positive 4. Why is it positive 4 here? Because O is minus 2 would be x minus 4 equals 0. So x, of course, is 4. So that's what it's changing. All right, the very last one, and we'll call it quits. LL is solution of potassium iodide, solution C dissociated, K positive, plus I negative, is added to an acidified solution of potassium dichromate, K positive, plus Cr2O7 2-. I can't emphasize how important it is that you've memorized your polyions. If you don't know what dichromate is, you're basically hosed. So this is an acid. Okay, you should have memorized that dichromate in acidic solutions turn into chromium 3 positive. And so that's reducing, so something must oxidize. You might notice you got potassium twice. It's not going to happen. The I negative can turn into I2. Now balancing this is going to be a bit of an issue. Okay, so let's go ahead and do it. You got Cr2O7 2-. You have to do the half reaction method. Make Cr3 positive. You have to put a 2 here because that's always a common thing. A lot of students forget they got to balance that chromium. And then you're going to have to add some waters. You'll need 7 waters to balance off the oxygen in the dichromate, and that's going to make 14 hydrogen. That's a big number, isn't it? Now, what is going to be the charge on this left side? You got 14 from the hydrogen plus negative 2, so that's plus 12. And on this side, we've got, now this is, a lot of students miss this, they got the 2 of these, that's going to be plus 6. So you're going to need 6 electrons on this side. Now in the iodide reaction, the iodide is going to turn into iodine. You'll need a 2 here, plus 2 electrons. To balance this, you'll need to multiply this one by 3. And so that's going to make my numbers here, this will be a 6, and this will be a 3, and of course this will be a 6, which I want to cancel out. So my final answer will be 14H positive plus the dichromate Cr2O7, 2 minus, plus 3I negative makes 3I2 plus 2Cr3 positive plus 7 waters. There's a long one, huh? All right, now, what is the reducing agent? Remember, reducing agent would be the substance that is oxidized, right? That's the one whose charge goes up. Or you might, do the Leo goes Gur. Oxidized is the one who loses electrons. The one losing electrons, the electrons are leaving in the second reaction here. So the iodide is the reducing agent. Or you could think of his charge as going up. So, yeah. Okay, well, I hope that you enjoyed the podcast. If you have questions for me, I would be glad to answer them. Put my email address up on this next screen. So it's jbergmann at Woodland, WPSD, Woodland Park School District, K12.org. And you can go to my webpage for more information. That would be www.wpsdk12.org. Backslash, there's a little tilde, and it'll be J. Bergmann. Bergmann has 2 N's. Watch that. Have a great day. We'll talk to you.